First paper was VLM, and the motivation goes here. Open source. There are many open source LLMs, but their knowledge station is done mainly on forward scale divergence. So this paper proposes a different way, reverse scale divergence for more effective mode seeking distillation. So for this, doing this reverse scale divergence, the paper will also go through policy gradient optimization. Next slide. So why reverse scale divergence? Standard scale divergence just forces the student to cover teacher through all the modes. That is like averaging all the modes of the output. But the reverse scale divergence forces the student to cover the it's like the mode seeking distillation behavior of this. Here reverse scale divergence is given as scale of q theta 1 p. Where q will be student model probability distribution and p will be the fixed teacher model probability distribution. So the objective here is to minimize the expectation of q theta, uh, expectation of q theta, y over q theta of log of q theta by p. So why it is difficult to optimize? Actually, the student model is still learning, and we cannot go through all the model distribution which will be given as output to any x input. In normal forward care dimension, this is just a like supervised. This is standard supervised because the parent output is fixed and we can easily find it. So here the paper proposes a way to handle this. Next slide. So the solution this paper proposes this problem as a reinforcement learning problem, and it this converts this problem to next reinforcement learning problem where the state is given as context and the current y prefix. It will output a prefix token, so it will output a y where the current prefix tokens will be y less than t, and action will be next token yt, and the policy will be q theta yt given y less than t and x. So according to policy gradient theorem, which they mentioned in the last of the derivations, the delta theta of L theta is given by uh, this is summation of all the tokens rewards. So this is basically the rewards of every token, and every token reward is given as the future rewards they will be getting by fixing at that position, and into delta theta of log of q theta. So it can be understood as a reward into delta of log of q theta summation. Next slide. Previous slide. Previous slide. So the paper, yeah. So it will do Monte Carlo simulation on the all the outputs. So it will just convert into reinforcement learning and do the random sampling over q theta, and that is problem they optimize. Uh, uh, and at last they did some minute optimization that I will. this is the critique. I am not still convinced. They just expand so to reduce. They just mentioned that it is high variance problem even if we do random sampling. So they distributed into some delta L single and delta L long. Delta L single they study about the current token, and then rest they told this is lesser variance than the previous. Mode why gave this previous one. In reverse KL division, it will mostly go to the higher mode, but in normal KL division, if there are multiple modes, it will try to cover all the modes. Okay. Adapt. This present to the problems. The micro policy variance theorem. So till now we are not done with this Monte estimation which they did. This is just they did like Monte Carlo estimation. So it is a high variance problem. And the second problem is that Q3 since the student is learning from its model distribution, so it can happen in some sentences like the reward for certain tokens is high. So the student can hack those rewards and can just go to low quality generations. And the third problem is length bias. There are always a length bias because rewards are given on the future tokens. So the last token will get the least reward. So the uh, student will try to converge to shorter sentences. So to address these problems, they address three techniques. Student problem is estimated as reward into delta of q theta log q theta. So if the for the last token the reward is least, so they will not try to learn over the long sentences. They will try to shorten it. So to optimize this problem, they presented three techniques. First, to address this high variance, length bias. It will not like for a target sequence length is this much. So it will try to converge into smaller sentence. It would not give much long sentence. So to first enhancement is single step decomposition. For delta theta they propose, we convert it into single and long. The single is just next token. So this next token reward they calculate as over the vocabulary set. It is just a problem of estimation, expected estimation of all the vocabulary words that will set at that t position. So this term becomes fixed, and this is again the sampling over y. So in the paper they told that they reduce this high variance to somehow fixed and low variance. Next slide. So to address the problem of reward hacking, they did converted delta L theta into delta L single, then token reward, and previous, previous, delta L single and delta L long. So current reward they will focus more and its fixed value, and the delta long they are now all sampling only. Uh, hmm. Yeah. Yeah. So the next problem was reward picking. So they did optimize this feature with uh, what they want to do is that the student model should mostly train over the parent model. So they define the weight as q theta over p tilde, where p tilde is defined as parent and student model sampling. So if the q theta is mostly like p tilde, this will mostly be 1, and weight will be defined accordingly. And both weights will be just multiplied with the delta single and delta long. Next slide. So for length normalization, what they did is that for the last token, this reward should be max. So they applied a weight t minus 1. So the last token it will be 1. But for the previous tokens, this weights will tend this reward to be smaller. So now they will try to tend for the longer sentences, and the overall delta and theta will become like this. This is the term of delta and single, and this is delta L long. And they replaced RT plus 1 with RT plus 1 norm, which is defined as this. RT plus 1 was just summation of this. RT plus 1 norm is a weighted sum of this. So this is our final optimization which we have to do. Final delta L theta. This is the training algorithm. So for the student, they just first fine tuned with the cross entropy loss, and then over the prompts of X, they found the random sampling fit area. They gave weights and multiplied with delta L single and delta L long, and they convert if there is a pre-training loss, then add that. Otherwise, the total loss is delta L single plus delta L long, and that is updated. Next thing. Over the experimental results, they chose teachers models like GPT. Okay. The main analysis part is main. So this was actually used to should be the first slide. This is multiple mod coverage, and the forward care will converge here, but with the reverse care we'll use this mode seeking here. Now, average of all the modes. Analysis part. So the analysis part they distributed in 4 parts. That if the teacher size increases, this is the main kit. So if the teacher size increases, then this this mod mini LM score also increases. That is one nice difference. And then with the length of longer sentence, mini LM performs better than normal KD and sequential KD. This was a good inference. That over length it is perfect. And this is like bias, exposure bias, and this calibration error. Next. This is just same. So here the final contribution is that they prove that they defined a KD method which is better than normal standard KD, but it is highly on compute, based on highly it has high variance and major compute than normal KD.
Our second paper is based on the my second paper is this branching net paper, which is fast inference via early exiting from deep neural networks. And the motivation that they mentioned in this paper was that deep neural networks are becoming more and more accurate, and they're stacking many layers, and this is increasing the latency and energy usage. And in many cases, what they found is early layers are good enough for the classification. And the key idea here is to add early exit points, which are branches with deep network within these deep networks to reduce the computation for easy samples. And the branch net overview is like it has a like there's a deep neural network model here, and within this model they are adding multiple branches in between, and each branch can have subset of some layers, and we each can have sub branches as well. But in this paper, they are only considering a single branch. And here the mathematical details are X refers to input sample, Y is ground truth level, and F exit is the exit function, uh, and Z is the out F exit, which is the raw scores, and Y hat is the softmax of it. And in this paper, they are using cross entropy loss. In this paper, they are using cross entropy loss to and they are taking the weighted sum of the cross entropy loss at each of the exit points, and they are minimizing on it. And for the training method, the paper suggested using stochastic gradient descent with Adam optimizer. And in this algorithm, yes. Yeah. Oh, this W is the weight that is given to the exit branch. It's hyperparametric. Yeah, it's not. We need to tune it. Yeah. No, it's not at every layer. There are only select branches, certain branches. All the loss of each branch exit. No, each branch, sir, like each exit. Yeah. No, branches are selected at some nodes, not at every node. Like if you go, yes. Yeah. I mean, in paper they mentioned that these are some design choices at and go to the last later slides. And they found the, I mean, these are the experimental results they found on branchy linet. They found the accuracy to increase slightly and the speed up to be 5.4 times, and Alex at 1.5 times, and Hescat they found 1.8 times. We are not. Yeah, we are making on first paper. Yeah, here they mentioned that the PN and like the threshold and weights of each thing are hyperparameters, and they mentioned that the weights are not same. And second, yeah, and the hardware impact is that is, and the one.
So I'm also presenting a paper on early exit. So here early exit is based on transformer type architecture, but and here we so again the BERT models are computationally expensive and it takes a lot of time for inference. So the already existing early exit methods are kind of limited to classification type models because in classification we kind of use the entropy of the output distribution we obtain. So it is limited to classification, and we in this paper we propose and we in this paper we propose a new fine tuning strategy to train the weights, and we also extend the support from classification to regression based tasks as well. So this is the bulk architecture, and as you can see, it is an encoder only architecture, and which is used for
say class prediction tasks and so on. So at after each encoder layer, we take so after each encoder layer, we have a hidden state I, which we define as HI. So this HI, so we add a LE exit after each HI present here and so on. So we add a classifier at each layer. So if there are total n transform layers, we will have a total of n classifiers to be added for LE exit. So again, we just define a loss function for at each layer. So it might be a cross entropy loss or mean square error loss, depending on the task, whether it is classification or regression. So now we need to train this network. So to train this network, there are three methods proposed in the paper. The first method is just using the sum of all loss functions. We call it as a joint strategy. And second method, where first we need to train the last classifier ln and train the entire model based from this ln and freeze the parameters of the transformers, the weights of transformers and the classifier. And in the second stage, we take the sum of losses of remaining n minus 1 classifiers and find the weights of these n minus 1 layers classifiers. So, yeah, no, we freeze all the first. So basically, we train the backbone network first and then train the remaining n minus 1 classifiers together in stage 2. So it kind of gave better performance for larger exit layers. So by larger exit layer, so we keep a performance for each layer, whether it's giving accurate results or not. This method gave better results for larger exit layers to exit at larger layers. So this is such last layers. And the first method kind of gave uh, same results across all layers. So joint running, just using joint running. Yeah, it's kind of similar compared to the next method too for larger exit layers, but which is not the goal of early exit. Theta is the parameters of transformers. T is the classifier at is. Yeah. Oh, combining these two methods, they proposed the main method, which is the method. So again, it's also not kind of too novel. They while in the training loop for odd iterations, they train the only the nth classifier, and for even iterations, they train the summation of all n classifier losses. So this is the strategy they proposed, and this performs better and give decent results compared to both strategies. So yeah. And so again, we already told that we will extend the support to regression based tasks. So yeah, that's what exiting decision. That's what I'm doing. Okay. So first we define a confidence level at each layer I. So to measure the confidence level, so the method which was present in the branch net paper or all other paper is just calculating an entropy of the output distribution present. So this paper they proposed it instead of using a predefined function like entropy, we train the function which we use for the measuring the confidence level. We just use a single fully connected network called LTE module, and we initialize the CNB parameters and train these parameters along with the classifier model, train this LTE network. So for training, so we will add another loss term. So instead of currently we have at layer I, we have a cross entropy loss or regression based loss defined on classifier, and we define another loss Ji, which is the UI which we obtained from the UI, which is the confidence we obtained from the LTE network, and UI hat, which is the ground truth label which should happen. So for classification task, the UI hat is just if the layer predicts correct label at layer I, the UI hat will be 1. Otherwise, the UI hat will be 0. For regression based tasks, they define a tan h function, like they define a function based on 1 minus tan h of, and this is the output of the classifier. So it's a regression model, but we call it classifier, and y is the expected value which we need to have. So we try in this JI of writing LI, we just write LI plus JI in the previous methods, alternating or two stage or joint training. In all methods, so instead of training UI hat, so UI hat is the ground truth label at this layer, whether we define. So not that kind of. So UI hat is not ground truth. The ground truth label is y, which we need, which we are expecting. UI hat is some other value which is measured used for calculating loss. So some kind of expected value which we need to have. Yeah, y. So some kind of expected confidence of this expected confidence at layer I. So for classification tasks, it is more intuitive because expected confidence is UI hat should be 1, that if the expected output matches the correct label. Now, so classification is just 0, 1. For regression, they define a function. UI hat. Some value we define for classification task. It is just it is the confidence level which we need. It will be 1 if the expected value matches the label. It will be 0 otherwise. Yeah, UI is the confidence we measured from the LTE module. So to train this, instead of having LI, just replace LI plus JI in all layers and use the previous methods. Yeah, yeah. I don't think they mentioned anything related to that. They just said replace with LI plus JI. So in the experiments, 0, 1, not expect. Yeah. Hmm? We can add expression of LI is just LI is a cross entropy.
LI is mute. Not mute. Just turn off the speaker.
You speak it down. Yeah.
So LI is basically of the nature of cross entropy.
Yeah.
And it is not with respect. It's with respect to all the class labels. I think we'll run out of time. But it's over all the class labels, right?
Yeah,
It's cross
over all.
entropy over all the class labels. Whereas GI is a binary thing almost, or with a little regression flavor. LI has a probabilistic term also, is it? Yeah, but it scales with the number of classes, right? Whereas the other term won't scale with the number of classes.
We
Like
can
find
divide by
always.
mod.
Huh?
I mean, we can divide by mod number of classes for this to normalize it.
Yeah, so do they
Yeah.
do that is the question.
Yeah.
See, this is optimization course. That's why these questions are even more important. So you should give some thought to it. So your optimization students, yeah, at least that due diligence has to be done. I mean, feature engineering, if here and there, it's fine because we are not a speech course. We are not a right. Optimization is very serious. Go ahead. So you need to figure out what the trade-off between LI and GI is.
So here are the results, like the two-stage performance.
You can skip the results. I mean, we are running out of time, right? So
that's it, the conclusion.
So by fine-tuning, alternating, and using
I
LT module.
start using LT and
So LT module is just to get the exits. Otherwise,
exit the measure the confidence level at
confidence.
the layer.
Otherwise, the alternating strategy itself will is giving them gains.
This is giving them better exit results. Early exit.
So did they do the following? Did they do LT after alternating? You find LT.
Yeah.
And then use exit only from the LT. Use confidence threshold based on prune based on confidence.
Yeah, that's what we do in inference. Like
they did that.
Yeah.
So that improved also.
No. Like inferencing is already done like that. When the confidence value which we get from the LTE network is greater than some threshold, we will exit or something. So we do like that.
Acha. So the results are with respect to LT. I see. Okay, got it. So what's your project?
So again, we are using the similar type of architecture of bird based architecture to Mamba based architecture because and so this is the similar level. So we have a Mamba layers 1 to n and use almost same architecture as add an exit head, measure across entropy, add a confidence, and we do a knowledge distillation from each exit head because we have an output from each layer. So we do a knowledge distillation from each exit heads and do some weighted sum, or for currently we're just thinking of adding all these loss terms together and training it based.
Yeah, but I think the last paper was certainly very interesting. So you may want to consider baseline building on that. Okay, this is your weighted.
Like currently these lambda values, we are thinking of keeping them as 1, or depending on ratio of losses which we get, we tune the lambda values.
I would suggest because even the last paper we had the same problem. What the lambda should be scaled. So give some little bit more thought to those, the first and the last paper at least, including some good things to learn and some limitations with each of them.
Thanks.
That's the reason project builds on seminar, right? So you should not just throw away the seminar when you start doing the project.
So mainly on third, we are planning to include the first paper if possible, like adding reverse scale divergence.
Any questions for them as the next team sets up? You can. Any questions?
Our